Hello, welcome to Remote Controls, creating reliable shared screen games with multiple input devices. I am your host, Tim. I'm a freelance game developer from Hobart, Tasmania. That's the little island down the bottom. If you've not been there, it's lovely. Hopefully one day you'll be able to come visit. Now, I'm going to say the term I a lot while talking about this. However, no man is an island, unlike Tasmania. So I did this with a bunch of other people who were all part of the project. Extra special shout out to one of them, John, for letting me borrow all of his cool AV gear. So we're going to start this story, where all good stories start, in the beginning. This is a tale about an educational game for children. It was designed to teach certain curriculum outcomes around geosciences. This meant it needed to have very specific scenarios that it needed to hit and information it needed to deliver. So we're somewhat limited in the scope of what we can do, but this also made it a very interesting project. Now, the core of the project was to be 8 little mini games to be played in classes cooperatively. They were to be under the guidance of the teacher, so some things that would be a little bit weird and otherwise wouldn't work in a game would work fine because the teacher was there. They would have a single shared display at the front of the classroom, and you would have 6 to 8 students playing them. Now, that's not a full class, but the idea was you could play multiple rounds of these games. Now, by the time I got involved, the games were already partially designed, and those that weren't partially designed still had specific outcomes they needed to hit. So there was always a guiding point at every stage. Now, we were told very early on that the classrooms themselves would have a projector and a computer, or a large screen and a computer, which would essentially be the target device that we'd be running the games on. So our initial thoughts when we went to the client is, hey, so let's just buy a bunch of Xbox controllers, plug them in, we'll make the games, it'll go great. That way you only need a single USB hub and a gaggle of controllers. And it's at this point in our story, along comes a wrinkle. So we're now informed by the client that we're not allowed to have any new hardware added into the classrooms. We had to use the students' devices for any input. The reasons for this are not entirely clear. Presumably you cannot require schools to add new hardware, which feels somewhat reasonable, if a little weird. I do think now, having known the client a little bit better, we probably could have pushed back on that and actually got the controllers. However, that would be a much less interesting talk. So anyway, we're like, all right, student devices. So we go to the client and we go, what about Bluetooth? And they go, no. And we're like, okay. What if we create a local Wi-Fi network? And they go, no. And we're like, cool. So no Bluetooth, no Wi-Fi. So we go, okay, what can we use? And they go, the internet. And we go, the internet? And they go, the internet. So I'm not entirely sure why we can use the internet but can't use anything else. Again, this might just be another one of those schools have very particular requirements. It may even be weirder than that. I don't know. But we found ourselves now having to make a local shared screen co-op game that goes over the internet. So not really a local co-op game at all. However, we go, all right, we can work around this. We're Unity developers. We can make a really interesting little client that will run on the phones, the iPads, the laptops that the students already have access to. It'll be great. It'll work. We'll get this nice sort of lovely environment. We take this client and go, what do you think of this? And they go, no. And we're like, why? We didn't actually say it like that, but why? And they go, you cannot require the student to install software on their devices. And again, I can see why that is a concern. So we're like, okay, all right, what can we do? And they go, you can have a web browser. And we're like, cool, a web browser. Okay, so at this point, we're stuck in this sort of a weird place. And we go, all right, so we'll make it so that the students will go to a website, they'll punch in some sort of magic code, and then that will give them the inputs they will need for their shared screen game. Now, for some of you, you might be going, hang on. Isn't this just Kahoot? Now, for those of you who don't know, Kahoot is actually a very similar idea and even has a lot of similar goals to what we were working on. Teachers can design these sort of multiple choice, or not even multiple choice quizzes, which they can then even share amongst other teachers. They send their students a code, they put that into the Kahoot website, and they get to pick from these multiple choice quizzes. It's actually a pretty cool little game. In fact, it was even listed as one of the inspirations for this project. So that sort of begs the question, how is our idea different? Well, the main thing is Kahoot is designed around multiple choice quiz sort of questions. That's its real strength, and that is where all of its assumptions lie. So even though there is a shared screen which is viewed by the class, it sort of is not the main focus. Whereas what we're making is an interesting shared screen event, and then the students are just controlling it sort of remotely. So we effectively had custom game by game basis, where Kahoot just has custom quiz by quiz basis. And we had this problem. We had to design 8 games. 3 of them are real-time or near real-time, and 5 of them are turn-based or simultaneous turn-based, which is a really good time to talk about the games themselves. So at this stage, it's worth, just before going any further, saying that these games are actually, as we're about to describe them, in their post-iteration stage. So this is after we've already had the "that's impossible" with the client discussions, as well as gone through some sort of back and forth tweaks that needed to be changed regardless. However, for the most part, the games actually didn't significantly change from the client's initial design briefs, and I think that's actually to their credit that they came up with some relatively workable ideas right from the get-go. So let's get started. This game was all about trying to teach the children about the interaction of stromatolites and anoxic microbes and their impact on the early Earth's oceans and atmospheres. The goal at its core was pretty straightforward. It was to stop the anoxic microbes getting past the defensive perimeter, effectively, of the game. Now, this was one of the few real-time games that we had. So you had to sort of have some coordination between the different players to make sure that you stopped as many microbes as possible. Now, on the students' end, they basically just had like a shoot oxygen button on their controllers, which they would be clicking, shoot, 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 shoot. The timers did exist, but for the most part, they weren't actually on the student couldn't tell the timers. It was all on the main screen, so they had to look up to make sure that they were able to take the action. And the idea of this was to try and force some cooperation amongst the teammates instead of just, mashing the shoot button constantly. This game is one of my favorites. In this one, we have the entire class cooperatively controlling a submarine as they move around the ocean floor. The goal of this game is to use the various sensors on the submarine and to work cooperatively together to discover geothermal vents that are on the ocean's floor. I now know way too much about geothermal events at a level required for students, so if you need to know something about that, do ask me. The really interesting thing about this game is it had a lot of various interesting interactions between the players, because each player could only do things depending on what the rest of the team was doing. So as an example of this, if, say, the engineering department had not given power to ops, they couldn't do a ping, so you couldn't tell what was nearby. And that was the entire core of the game. While it was to teach this sort of aspect of geothermal vents using sensors, they had to work together to move the submarine. As a side effect of this game actually had a lot of various dynamic UI, where buttons and labels had to be updated on the students' devices so they could actually see what was happening. We also had these 3 narrative games. These at their core work sort of similar to your traditional Telltale style dialogue game, where you had a conversation with various characters in a world. Now, unlike a Telltale game, it was a little bit different in that all of the players were cooperatively voting on which decision to make. So there was sort of still a cooperative element, and you did have to have this discussion between the different students to decide which option to vote on. Despite this game looking a little bit like Mini Metro, it's actually nothing at all like Mini Metro. In Mini Metro, you actually design the rail lines yourself, whereas in this game, you actually control a train. This game's design was to try and teach the combination of logistics and coordination. And basically, the goal was to sort of move your cargo from one point to the port and then back and keep going like that to get the highest amount possible. This was another very reactive UI heavy game. Mostly because after moving, you really needed the game controllers to update to say, hey, I need to go here now. So you actually had to have that sent over. In particular, when you had to load or unload cargo, you needed the buttons to know about that, so that way they could correctly update. I really love the UI of this one because it sort of looks like a bad 1995 control box. Internally, we called this game Crane Game, and it was all about a combination of teaching coordination, cooperation, logistics to some degree, and also the basics of propositional logic. While I absolutely love the UI, the real thing I love about this game is the fact that it is by far the best example of, I think, what we were trying to go for here with our architecture, which we'll talk more about in a little bit, in that the game sort of didn't really care about what anyone else was doing. From an input perspective, they just had to worry about their own thing. They still required a lot of cooperation and coordination amongst the students because each person, while they could either move their crane left, right, or load it, they did have to worry about what the correct thing to do at any time was. So there was a lot of coordination, but from a network or gameplay perspective, there was far less, which I did really like. It was like probably my favorite sort of example where the code was pretty much spot on with what we were going for. This game we called the coring game internally. And the purpose behind this game was to try and teach sort of chemical observations and deductive reasoning of minerals. Now, sort of much like Crane game earlier on, it was reactive to some degree, but very, very minimally reactive. And likewise, it had a lot of sort of code that I actually quite like as to how it turned out from a program perspective. The thing I actually really like about this game the most, however, was we didn't stop anyone making wrong decisions at any time. In most of the games, you couldn't really make a wrong decision as such. Like, there was always some sort of payoff for doing things. Whereas in this game, if you pick the wrong thing, the game ends and you have to keep going. So there was sort of this aspect of where you could actually have players kind of be jerks and like deliberately pick something wrong. We don't know if anyone ever did that. We didn't see anyone ever doing that, but it may have happened, and I did really like it because of it. So it forced a lot more discussion into the class, because if you made the wrong decision, you're making the wrong decision for everyone. Other than that, however, it was sort of at its core basically a little mini quiz game. Overall, while these games themselves seem pretty straightforward, the project as the whole actually had a few very unusual quirks that very few games get to have. Now, co-op games aren't new. They've been around for a while, and even the idea of games which are meant to go into a classroom aren't particularly new. But because they had to go into the classroom, the focus definitely had to be on the shared display, what everyone could look at and sort of interact with. And each game was for 6 to 8 players, so we sort of had, we have examples of games that are similar to this, which we could build upon. But the real wrinkle in this case came about because even though 6 to 8 players is a kind of normal amount of players for a lot of co-op games, classes generally are much bigger than that. They tend to be 4+ times the size of that. So we were sort of talking to the client about this, like, hey, what do we do? And the answer that we were told is, it is expected that we'll have small clusters of students operating together as a single player equivalent. And the idea would be they would have their own little internal mini discussions before then participating in the group discussion. So we had this problem of the games also had to work in this weird context where you've got this shared display and the players, the 6 to 8 players who had to coordinate and cooperate. But then they also had to be able to flick back and forth between these sort of like mega players and also these little internal player clusters which they had to work together. And this sort of really stuck us in between sort of a design rock and a requirements hard place, which we'll talk about now. So these games are quite different from each other. 3 of them had a lot of similarity in the narrative ones, and we could reuse a lot of that, but all the other games were actually very independent. So we needed to work out a highly flexible system for building these things where the students would be able to control them without like overwhelming the work we had to do. So that is why I'm going to now go to Tim over in the architecture corner. Take it away, Tim.
Thanks, Tim. That guy's so cool. So welcome here to the architecture corner. Let's talk a little bit about the architecture of our solution. So directly above me here we have the game itself, which hopefully is pretty obvious what it does. Slightly off to the side we have the input system here. This is what handles any input from the network. So input will be coming in from the network and then passed on to the game. And if we take a little bit step further towards the internet, always dangerous, we find ourselves now at the network manager. The network manager is, as its name implies, responsible for managing the network. So any internet traffic that's coming through gets hit into the network manager here. It munges it, it deals what it needs to, and then passes it back onto the input system, which itself will then pass it onto the game. Now, you may notice the internet is way off in the distance. That's actually where it belongs. You should never be close to the internet. It's scary there. And hanging off the internet, we have these clients just, off in the distance there. Now, the clients in this case are very simple. They're just a web browser. with a list of buttons and other sort of related elements. And then anytime that a user, whether that be the student or the teacher, the clients were basically the same in both cases, they just had different buttons. It would then be sending these messages up to the internet. From the internet, our network manager here would be receiving them, it would be dealing with them, then it would pass them on to the input itself. When the input system works out what they are and converts them into useful input actions for the game, they then get passed on up to the game itself so the game can make some use of it. Now, you might be thinking this doesn't seem particularly interesting, and you might also be thinking, hang on, there's no arrows back the other way. How does anything talk to anything? And that is actually sort of the secret sauce to all of this. We came up with this idea for the clients, which we're going to call controllers. And this came about because we really liked the idea of, well, controllers, so Xbox, PlayStation, those sort of style controllers. And we really wanted to recapture that. We wanted our clients off in the distance to still work kind of like a controller. So we had to design a way around it, but we also knew we had to have the internet being scary and off in the distance, and we wanted to protect it all by having this sort of network manager here, which took care of everything. So we need to work out how we could do that. So what we came up with was, as I said, controllers. And by that I mean these clients, way off there, don't have any capability other than they just send, hey, button was pressed, button was pressed, button was pressed, and again, network all the way through. Now, that means they need to work out what buttons to press. Well, the way they get that is they do actually get that from the game. There is one arrow that we've not drawn on here intentionally because it's sort of, it's the dark secret, and that is when the game is configured, it then sends a message back through the network manager, which goes, from the network manager up to the internet and then over down onto the clients. The clients at this point are now controllers, and they get sent this configuration file. This configuration file has all of the information they need to know to set themselves up. So it gives them the button information, any labels, etc., what type of buttons, what they look like, so on and so forth, which they then get to press. And that's sort of it. That's the actual secret that we discovered. Thanks for joining me in the Architecture Corner. Back to you, Tim.
Thanks, Tim. So at this point you might be wondering, this doesn't really sound that advanced. What is so special about this? I mean, all you've really done is replicated the existence of controllers, except now they're someone's phone. And that is what's special about it. So basically we forced ourselves to keep the external input as straightforward as possible. They have no intelligence and no state as much as we could. This, however, made an interesting change in that it forced us to make the other elements of the game also stubborn. They had to do their one thing and do it very, very well. So we were basically forced by the system to do separation of responsibility. Now, we all agree as programmers, you should be doing this. You should have separate elements that handle separate things. However, the real world is generally not that simple. Your nice clean code interfaces tend to get polluted over time as you need to do different things. However, here, because our input system is reliant on a network layer, we didn't want to mix the two together. It's just asking for trouble if we did that, so we had to separate it. But then once our input system is now separate from our network system, it's also separate from the game system. So we actually had sort of these three different layers that did not talk to each other other than through these nice clean interfaces. So we basically were forced to break it all up because we had no other choice. However, this meant the game was isolated from its input system, which is very unusual. So it had the ability to receive input, but the input itself was imaginary and just generated by this thing that said, by the way, I have pressed button A, and so on and so forth. And because we mandated that the controllers themselves have no logic, then that means we were able to force all the bugs into one of the other layers, which are much easier to debug and control rather than just, it's an internet problem layer. Now, the really interesting side effect of this is having a super simple input manager. Because the input itself was just essentially receiving an endless stream of messages, the input system itself would then just spit out an endless stream of buttons for the game to consume. And in fact, it actually resulted in a simpler input interface between the game and the input system than if we'd got to use physical like Xbox or PlayStation controllers themselves. So what we have here is we have all input code is decoupled from what uses the input. That means we can simulate or generate test input and test input data trivially, however we wanted to. we could write our own heuristic input code, which is, me actually pressing keys and generating things. We could generate test data and have it fed into the system and actually work. It's kind of slightly hard to necessarily believe, but this made testing and debugging almost trivial in comparison to normally handling the input of a game. Additionally, there was no longer an obvious connection between the player as a concept and their input, because it all just sort of went into this pipeline of the internet and then came out the other side. This means a lot of gameplay decisions, instead of being connected to a player, got connected to an abstract system, which means we could reorder them, organize them, and control them how we wanted at the needs of the game at hand. This meant we actually found ourselves with less God objects. Now, we all agree we shouldn't do God objects, but we always make God objects. And that's because we were forced this separation of responsibility. Each different part of the game was actually easier to write as a separate element than it was to be part of player.cs or its equivalent. What I'm talking about here is we managed to trap all state into the game itself. So the actual code that managed the game was the only place where state existed. Nothing else needs to worry about or even know there is state. They're essentially given the idealized version of what we like to pretend we can write software like, which is where they have input, they do some processing to it, they give you the output. It was almost similar to writing in a functional manner, even though we weren't writing in a functional programming manner. Now, technically, there was some state inside the network manager for handling disconnect, reconnect, message replay, that sort of stuff. But even then, that was still isolated. It was state that it needed to manage the network, and it didn't have to pass that either to the clients or to the game. It had nothing to do with it. It was independent of the rest of the system, and vice versa for the game. So again, it is really hard to overstate just how, in comparison to other network things or other input systems we've ever used, how easy it was and trivial to actually debug this system. Unfortunately, it wasn't all perfect. Now, the main downside to this is reactive UI was practically impossible. So if you remember back to how we were talking about the architecture where the controllers get sent a config file, which basically tells them how they are to draw their layout, this was quite a big file, which means changing it was slow, and there's also just network latency to worry about. So making lots of little UI updates on the fly was not really possible, or if it was possible, it had some bad side effects. Now, an obvious initial fix to this would be partial updates. So just send over little tiny pieces going, hey, I need this button to read like this, I need this element to move, so on and so forth, instead of having to send this quite large configuration file every single time. But that means either the game now needs to know about the controllers and their current existing state, or the other way around, the controllers now need to know about the game so they know how to react correctly. And if we do that, we've suddenly just destroyed that lovely, nice, clean interface we just were raving about how good it was, where the game was separate from its input and the input was separate from the game. Because now everything's talking to the internet, and they're talking to the internet a lot more. The game is now talking to the internet. Previously, it never was. And we did have to do this in a few cases, and in those places, we found ourselves building more God-like God objects as a side effect, because it's just more convenient to put more functionality into it, and that's sort of what happened. Overall, what this means is games with reactive UI elements were the ones that had the most bugs. Now, we did still need to do it for some games, particularly the submarine game had a lot of reactive elements, as did the train game. The main downside of this was not necessarily the bugs, however, it was the testing, because suddenly we could no longer keep these nice clean layers, and all of our lovely testing that we were building up on the fly was useless when you have to have basically end-to-end working to get anywhere. You could no longer just query things, generate data as needed on either point. And like I said, the vast majority of the bugs that we had were in these games that had reactive UI elements. Most of these bugs were around desyncs. So either the game got out of sync with what the controller needed to know, or the controller got out of sync with what the game needed to know. Which means we did end up having to put some state in the controllers, which I still regret, but life is not perfect. In particular, most of what we did state-wise was we generated what we called one-shot buttons, which was basically just a modification of an existing button, but once it was pressed, it would delete itself from the UI. Now that doesn't sound particularly amazing. In fact, it sounds very obvious and straightforward, but it's actually more effective than we first thought. You can simulate a lot of interesting back and forth behavior just by turning off elements. And it also gives you the time necessary for the game to go, okay, it's now time to send another big config update, here you go. So they actually worked a lot better than I think we were expecting, and we started using them more and more as a way of sort of building lightly coupled dynamic reactive UI. Now, something that I find very interesting about all this is we are not the first people to run up against this problem, and we're not the first people to try and solve this problem. And in fact, there's a really good example of people running up against and solving this problem in a very similar fashion. And that is the Jackbox party games. Now, if you don't know, the Jackbox party games are a series of little sort of fun, quirky party games that originally, I believe, started as trivia, so just like multiplayer trivia games. Similar to Kahoot, you do have this sort of shared screen experience controlled by lots of independent, now mobile, but originally it was just web. It was probably actually Flash now that I think about it, originally, independent inputs. Unlike Kahoot, however, and much more like our game, the mini-games vary quite a lot in how they work and how they need to be controlled. Also, unlike Kahoot, they're a lot more, I guess, chaotic is the best example I can sort of think of in their nature. The games are also a little bit different from both us and Kahoot in they don't really, despite having a sort of trivia and quiz heritage, have any focus on knowledge. They're much more about having a bit of fun. They're a party game, as their name sort of implies. So they've got a real sort of family and friends, probably more friends than family focus. But there is still sort of this bias in their input system towards single button selection games. So games where you make a single or limited selection from buttons. Or something quite different, which I find very interesting about the Jackbox games, is they have quite a few what I'm going to call keyboard games, which is basically where you have to like just mash in an answer. Now there is one very interesting counterpoint to this, and this is the one I want to spend just a little bit of time talking about, and that is the game they call Drawful. Now, Drawful is a completely different minigame, I would say, from most of the other minigames in Jackbox. So like I said, most of the other ones are button press or keyboard games. In Drawful, you basically are playing a weird variant on Pictionary, is the best sort of description I can think of without going into too much detail. In Drawful, you have a lot more input and a lot more information that needs to be sort of passed around the world to make it actually work. You are effectively using your finger as a drawing stylus and your phone as a tablet. And you, like I said, you're playing a weird Pictionary game. So you're given some sort of input to draw. You got to draw it. People have to guess. It gets passed around. People got to make different guesses, so on and so forth. And because it's a party game, it tends to be a little bit silly, and the goal is to trick people and so on and so forth. The thing that I find interesting about Drawful isn't that it has a different input system. It's that, and I mean this with a lot of respect because I quite like the Jackbox games, it's a little bit clunky. Now, I think that's a side effect of because in a drawing game or a drawing system in general, you actually want basically zero latency between your actions and your results. You want to be able to see it, you want to be able to feel it effectively. And that is why sort of most drawing applications actually have very, very harsh requirements on their performance. Now, Drawful, because of its sort of nature as its heritage coming from these trivia games, I don't think their input system was really designed to handle this. Much like our input system is not really designed to handle heavily reactive UI. So they had this sort of problem where they had this game, and it isn't the best game in my opinion, that the input system didn't really work great for. So they actually did what I think is the 100% correct thing. They basically tore that mini game out and made it a standalone game, presumably with a completely independent input system that they wrote from scratch that worked very well for that instead of relying on this legacy system. And on their own marketing page for it, they even described it as, and I quote, "We created an even more robust standalone sequel." So the actual marketing point of Drawful 2 over the original Jackbox Drawful is it's more reliable, it feels better, it's nicer. And that's literally on their website. That's them telling the people who they want to by it, not like game devs talking back and forth, going like, yeah, I moved that 0.2, and people are like, 0.2, I love it. This is for hopefully normal people to actually get excited about. So it's a very interesting example because they hit the same sort of problem. The more reactive and the more snappy you need your UI to feel, the harder it becomes when your heritage is effectively buttons. But enough about the UI, let's talk about the networking solution we went with for a bit. Now, the interesting thing about most of the out-of-the-box or included with Unity networking packages is the thing they care about is actually object state replication. They care about if I make a change here to an object, it appears over here to this object and appears as smoothly as possible. And that's true whether it's UNet or the new one whose name I never remember the name of, assuming it ever comes out, or even most of the third-party ones out there. And they generally do a pretty good job of this. The thing is, we don't care about object replication. We have completely asymmetric controls. Like, the client is not running the same code or even cares what the game code is doing. So these sort of default out-of-the-box video game reliant network packages are not what we want. So we had to start looking a little bit further. And first place I looked was actually Google's Agones. I'm not sure if I'm pronouncing that correctly, which is a very interesting sort of product. It's actually very large and does quite a lot of things. And I was looking at it, I was like, this could be cool, but I think it's probably overkill for what we wanted. It feels more like you're making Among Us rather than a game that has to support, 50 people at a time. So like, not that it's a bad product, just it seemed too big and too scary for us. So we kept moving on, and that took us to just general purpose networking packages. In particular, we looked at a whole bunch, but we whittled it down to sort of two. I say we, I did all of this bits. This one's actually just me. I was looking at 0MQ and Pubnub. Now, there were more than these two. These two were the last ones to survive after whittling off others because effectively they're the biggest and the oldest, which means they're generally the most reliable and they had pretty good looking docs. So we're like, yeah, I guess this is it. Now, they were slightly different technologies, which is a pretty good diversion, I think, to just quickly talk about that. Now, as I said, we nailed it down to either 0MQ or Pubnub. Now, these are very different technologies. In the end, it didn't actually matter, but it's worth sort of talking about the differences between them, so if you ever find yourself in a similar circumstance, you can sort of make some decisions behind it. Now, the first one, a message queue, is, as its name suggests, is a queue of messages. Clients are part of the queue, and then they push messages onto them, and then the message queue system will, grab the top message off it, look at it, read who it's for, and then give it to them. So it's effectively targeted, but it is still a queue. Messages get added to the end and read from the front. Now, on the other hand is a pub sub, or publish subscribe system. Now, that's a little bit different in that it creates a bus that messages kind of get poured into. And then every time a message gets poured into, or at various different intervals as decided by the system itself, the clients who have subscribed to it get told about it. So it's a little bit more sort of scattershot approach. Everything gets told, hey, there's a new message in a pub subsystem, whereas a message queue is, by the way, this person has sent you a message. They both sort of have their own strengths and weaknesses. 0MQ, as its name sort of suggests, is a message queue. Pubnub is a pub sub. Glad I said that one correctly. Now, in the case of our project, it turns out because of the design we had, it didn't actually matter which one we had because all that mattered client-wise was the game. It was the only one that mattered. So if we had a message queue, they'd all be sending messages to the game. And if we had a pub sub, they'd all be sending messages that only the game would be listening to. But either way, they are very technologically different. It's just in our case, it didn't matter. However, in your case, it may. But now it's time to work out which one should we go with. In the end, we went with Pubnub over 0MQ. And we went with Pubnub for a variety of different reasons, despite the two of them having a lot in common. Both were very low cost, both had good documentation, both had support for various different client types that we needed to worry about. The main reason we chose Pubnub was because it has a heavy focus on reliability of its messages. And it was a little bit older, which we hoped meant because it had stuck around for longer, maybe it was better. So we did sort of roll the dice there, and we hope it worked out okay. Now, there was one big downside to Pubnub, which didn't affect us in this, but is a problem if you were to use it for yourself in some circumstances, and that is it has to go over the internet. It cannot be done locally, which ZeroMQ can do. You can run your own sort of servers of that, whereas Pubnub does not support that. They're a as a service sort of tool. In our case, that was fine, but it may not always be the case. Now, I would say, based on the project, Pubnub was definitely the right choice. We found that it actually had surprisingly good latency, despite not promising great latency, and in fact, you can even pay for better latency turnaround. Its libraries for both JavaScript and C# worked really, really well, despite some of the docs being a little bit annoying. They did still have a lot of docs, and they did still have a large community that you could sort of find answers on Stack Overflow for. Pubnub was just kind of impressively reliable. I think we were all very blown away, especially John, who did all the networking code, at how reliable Pubnub actually was. And in fact, it was so reliable, we found ourselves using more and more of its features and relying on it more and more. In particular, its ability to handle disconnects and replays and that sort of stuff for clients. If they dropped off, they could reconnect and then get the messages to get them back up to date. I know I keep saying how reliable it was, but it was kind of weirdly reliable, impressively so. It's probably the most reliable networking situation I've ever found myself in. In fact, we never had any bugs which was related to the networking side that either weren't us or weren't the network being down. And that gave us a weird amount of freedom for doing things that we were not expecting. It was weirdly nice to know that the void that you were screaming your messages into was actually going to pass that message on later to someone else, which is not something I've ever normally got to do with a networking sort of project before. And this had some very interesting implications, and it's for that very reason why we started implementing the one-shot buttons, because we effectively knew the message would get delivered and it would all be handled when we had to do the updates a little bit later. So it was actually very freeing in many respects. So I would say if you do need a network which is high reliability but perhaps not the highest of speed for your game, I would highly recommend taking a look at Pubnub. So to summarize, we had to make a series of shared screen co-op games for kids to learn certain things about geosciences. We needed to use the students' own devices as the means of input, and all communication had to go over the internet. We decided to keep the students' devices as simple as possible, to track no state, to have no updating as much as possible, to be as close to an Xbox or PlayStation controller as we could get it. That meant they would merely be told what to show, and then they would send over these update events. These events had to go over the internet, which we did by using Pubnub to deliver them to our game. The decision forced a separation on everything in our game, which we know as programmers is a good idea, but we can rarely find ourselves with the ability to do it. The internet controller design, however, skips over this hope and dream and just forces it on you. To steal a phrase from Tim Ford, it was a pit, but a pit of success. We were trapped in there, but it was a good pit, so we didn't really mind. This all led to the game code being nicely isolated, nicely testable, nicely debuggable. This works so much better than I expected. I'm going to try and reproduce it in other games. Even if I'm not doing something networking, I'm going to basically try and put an imaginary input shim in front of everything so I can fake it all. I want to get back into that pit. It was nice there. So if you ever find yourself in a situation working on a game where you have asymmetric clients or where you need a controller that can do slightly more than you think, highly take a look at Pubnub, highly take a look at putting yourself in the pit. Thank you.